this way. This is nothing but the usual kinetic energy expressed in terms of the scaled variables, which are basically the crystal coordinates in a cubic system, and then he added some kinetic energy for the cell with an additional parameter, this cell mass, that is a fictitious parameter that should be chosen in such a way that there is a good coupling between these two sets of variables, so that the typical fluctuations in the cell are happens on the same time scale as the typical fluctuation in the internal coordinates, so that there is a good exchange of energy, equilibration of energy between the different degrees of freedom. And then here you have the enthalpy, the electronic enthalpy. Parinello and Raman, shortly after, introduced the shape of the cell as variables, not only the volume but the shape. This H is basically the matrix of the three fundamental lattice vector. A variant of this, which has some advantage, is in certain cases has been developed by Renata Venskovic. That basically is the same, except that a different definition of the kinetic energy of the cell is given. And so from that you derive the Euler-Lagrange equations, and so you get the equation that you need to solve in the molecular dynamics. I will not tell you anything about MD anymore. The only thing that I will say is that you can try to use MD as a tool for optimization. So using this damped dynamics, I will tell you about this method in the context of variable cell shape, but this is the same thing that you can also do for normal, fixed cell optimization. The point is that if you let the system evolve, then you start from a configuration in which you have a certain potential energy and zero kinetic energy. Then the system evolves, will transfer some of the potential energy into the kinetic energy, and then will evolve conserving this total energy, kinetic plus potential. But if you find a way to drain out kinetic energies from the system, then eventually you are actually draining all possible kinetic energy, and when the system goes into some local minimum, then it will stop, because in any direction it would move the potential energy would increase, but he has no kinetic energy to exchange, and so with potential energy, so he will stop. So one way to drain kinetic energies from the system is just to add some friction. So you can move the ion subject to the force plus some term which is proportional to the negative of the velocity. Or another possibility is what is done in this quick mean, that you let the system evolve freely, but whenever, let's say, by free motion you overshoot the equilibrium geometry, and so it happens that you have that your velocity points in one direction and your force would point in the opposite direction, then you feel the velocity. Okay? So in one dimension that would basically drive you directly to the minimum. So you move faster and faster toward the minimum. When you overshoot the minimum, you kill the velocity, and then you go back a little bit, and then you have arrived. In more dimension, this is not that simple, and so it takes more than what it would take in one direction. But the idea is that the same. So you kill any generalized velocity component whenever its direction is opposite to the corresponding generalized force. Okay. How do you compare this with respect to the FGS? Well, it's easy to implement, very easy to implement, especially if you already have a molecular dynamics code that does that. It's rather robust in the sense that it is very simple and not many things can go wrong. Does not assume to be close to the minimum. Okay, so this works even if your energy landscape is not very quadratic. The downside of this is that you need to specify the time step because you want to integrate correctly the molecular dynamics. You need to specify in our particular case also this cell mass, which is some fictitious parameters that one may not be familiar with. So this requires some experience to make it work, and also does not exploit what BFGS and these other quasi-Newton-Raphson methods do. So does not exploit the knowledge, the accumulated knowledge about the curvature. I mean, something that is robust, does not care about the fact that the landscape is quadratic or whether it is quadratic, but so this means that does not exploit it. So close to the minimum, this tends to be BFGS tends to be more efficient. Okay. Anyway, what do you need to do if you want to do this kind of calculation? For instance, at 40 GPa. So this pressure is given in kilobars. So 400 kilobar is 40 GPa. You need to specify the serial act here. You need to specify which kind of damped dynamics you want. In this case, damped Ventskovich version of damped dynamic is defined. You need to specify a time step, which is here, 70 atomic unit, and you need to specify a cell mass. This input works, and then one can play around varying the dt and V mass and see when the integration of the molecular dynamics code get into trouble. So it requires a little bit of experience, which I don't have so much. So this one is working, and we will see, I think, in the afternoon. So it is working. This is what happens. The output say that there is some kinetic energy. So this is the kinetic energy of the system. So this is a molecular dynamic run. So this is the kinetic energy of the ions and of the cell, the fictitious kinetic energy of the cell. Actually, it is mainly only the kinetic energy of the cell because the ions are fixed by symmetry, if I remember correctly. Okay, so this then can be translated in some kind of temperature, and this is the energy. This is not the enthalpy, this is the energy. And then things evolve, and let me see. Okay, there is no very big change in this thing, but basically this is decreasing. And yeah, this is decreasing. So this is suddenly at a given point and it has gone down by a factor of 10 from here to here, and then it will stop because the condition is met. Okay. And then what one can do is to do the calculation with BFGS, the calculation with this, and compare the final results and the interpret.
Okay. What is this temperature? T?
This T is the kinetic energy of the cell and of the atomic variables. So the system stops when the pressure and all the other conditions are met, even if the cell would have some residual velocity. Okay, So this is a molecular dynamic calculation. So you move, and the cell and the ions acquire some kinetic energy, and then you try to drain out this kinetic energy by this quick mean method. And by doing that, you approach, you confine your system around the minimum, and at a given point, the energy do not change anymore, and the pressure is within target. And at that point, the system stops.
But don't you think that this method is
Even if it has still some velocity and some internal and cell velocity.
But don't you think that this method is a little bit inefficient? It seems that after many self-kinetic calculations, the P pretty much stays the same, right? The stress.
Not within half a kilobar. Here, yes. Here it is below. It is within half a kilobar within to the target. The target is 400. So until you do not reach that, you keep moving. No. So when the pressure is 400 within half a kilobar, and the energy is not change within 10 to the minus 4, and all the forces are below whatever is the threshold, then it will stop. And that's what happens. Okay, so this is the end of this first presentation. So I think we can have a break, and then I will talk about the next.